All right, now let's look at some applications. There are two specific types of applications I want to look at. I want to look at measuring angles for navigation, and I want to look at area. Now, as far as measuring angles, now up to this point we've measured angles in standard form. In other words, we've measured them such that if I wanted to do a 60-degree angle, we would start measuring at the positive x-axis and we would go counterclockwise as far as desired, in this case 60 degrees. So starting at the positive x-axis, 60 degrees would be slightly less than a full quadrant, which would be 90 degrees. So this is somewhere around a 60-degree angle. Keeping in mind, this is 90, this is 180, 270, all the way back to 360, being equal to, or coterminal to 0 degrees. This is not the only way to measure angles. We call this standard form because this is the most common way to measure angles. All of our formulas that we use are based on angles that are measured in standard position, but we can measure it in any way we want to. Most commonly, when it comes to navigation, we use the compass headings to help us determine our direction, north, south, east, west. Now, whether you hear the word bearing, heading, or course, these all mean basically the same thing. They have to do with navigation. Now, occasionally you'll be given no direction whatsoever. You'll just be told that you have a bearing, a heading, a course of so many degrees. If you're not given a direction, then what you go ahead and do is assume that north is 0 degrees, and then you're going to go clockwise, so that east is 90 degrees, south would be 180 degrees, west would be 270 degrees, and of course back to north 360 degrees. Each direction is 90 degrees apart. So if I say ask for a heading of 60 degrees, well, we can determine a heading of 60 degrees since I'm not given any direction. I assume north to be 0 degrees, and I go clockwise from there. I'm going to go clockwise 60 degrees. Since it's 90 degrees to get to due east, then I know I'm going to be slightly shy of that. So this would be a 60-degree heading. In other words, 60 degrees to the right from due north. Now, this is nice, but it's not helpful when I'm doing all of my mathematical formulas, which are always based on standard position. So anytime I'm giving a heading, a bearing, or a course, I need to convert it to standard position, which really isn't that difficult. If this is 60 degrees right here, then this angle would have to be 30 degrees. Remember that a standard angle is measured from the positive x-axis. So when we're dealing with navigation, that just means we have to figure out where we are in relation to due east. Another way to do it is to give specific directions on the compass. For example, 60 degrees south of east. So instead of just saying a heading of 60 degrees, it says 60 degrees more specifically south of east. We don't assume anything. We are told specifically we are heading south of east. In other words, from east, we are going south. So I'm going to head south from east. So I'm measuring from east and I'm going down from there. So that tells me that this angle right here is 60 degrees, but now I need to convert it to standard position. Remember, standard position starts from positive x-axis, goes around counterclockwise. A couple of different ways I can do this conversion. I can realize that each quadrant represents 90 degrees, 90 degrees, 90 degrees, and of course this angle right here, if this is 60, then this would be 30. Added up, I get 300 degrees. Of course, the quicker way would be to realize that all the way around is 360, and then if I subtract 60, I would also get 300 degrees. Go ahead and give this one a try, a heading of 150 degrees. So if we have a heading of 150 degrees, that means we're starting with due north, and we're going to go clockwise 150 degrees. Well, from north to east is 90 degrees, which leaves me 60 degrees left to go. So 150 degrees would be in the southeast quadrant. Convert that to standard. Starting from the positive x-axis, going all the way around, 90, 90, 90. Now remember, if this was 150 degrees, that means this was 90, and this was 60, which really means this is the exact same as the last problem, 300 degrees. Give this one a try, 54 degrees west of north. So if we are 54 degrees west of north, we're in the northwest quadrant. and we are west of north, which means we are measuring to the west from north. So this would be 54 degrees right here. So to convert that to standard, let's go all the way back to the x-axis, tack on an extra 90 degrees to that 54, and we get 144 degrees. 36 degrees north of west. So we are north of west. We are going to the north from west, so we are measuring in this direction. This would be 36 degrees right here. So if we measure back to the positive x-axis, if that's 36 degrees, then this would be 54 degrees. 90 degrees, we are in the exact same position we were last time, 144 degrees. Also keep in mind, since we were measuring from west in this direction, we could have started with 180, subtracted the 36, that would have also gotten us 144. Let's apply that to a word problem. Now normally you would be given the picture and then asked to solve from there, but this one I wanted to go ahead and go through the whole process of drawing the picture just for fun. So we have from Tower A forest fire is spotted at 41 degrees west of north. So we have Tower A, we have a forest fire, and it is spotted 41 degrees west of north. In other words, it's not due north, it's 41 degrees west of north. So let's move Tower A off to the side, and then we can draw in our 41-degree angle by drawing in first a north-south line. There's our line of sight, 41 degrees. 41 degrees west of north. Now we also have Tower B, which is 12 miles and 87 degrees west of north of Tower A. So it's 12 miles away, but it's not on a due east-west line. It's 87 degrees west of north. So again, Tower B is going to be slightly to the north of Tower A. So let's move it up a little bit, and we can draw in our 87-degree angle. Now I can keep going. Tower B spots the same fire 15 degrees east of north. So here's Tower B spotting the same fire. Here's my due north line, and I want 15 degrees east of north. And how far is the fire from Tower A? That means we're looking from A to the fire. We're looking for this side right here. All right, so now here's all the information from the problem, but in order to solve the triangle, I need to know the angles on the inside, not the angles on the outside. So we can work our way around to help us figure out the missing angles, starting with this easy one over here. If the whole thing is 87 and the outside is 41, that means the inside is 46. So we've got 46 degrees on the inside right here. Now let's figure out the angle over here. We can't do the same thing we did over there because we don't know how big this angle is. It's not 90 degrees because this was not an east-west line, but I can use that concept to kind of help myself work around. Let's start by drawing an east-west line from Tower A. If this was 87 degrees, that means this angle right here would be 3 degrees. Now I can do the same thing from Tower B. Let's draw my east-west line. If this was 15 degrees, that means this angle right here would be 75. But there's still a little bit extra down here. To figure out what the extra is, I can realize, hey, I've got a east-west line, another east-west line, and a line connecting east-west line to east-west line. In other words, a transversal. These two angles right here are alternate interior angles. Alternate interior angles are congruent. So if this is 3 degrees, then this angle up here is 3 degrees. So that means 75 and 3 would be a total of 78 degrees. I now have all the information I need. Let's get rid of all the stuff that I don't need. For example, this, and this. Let's just focus on what's important. I realize that this is angle, side, angle, so I can use the law of sines. So why don't you take a moment, use the law of sines to solve the problem. All right, if I'm using the law of sines, that means I need to know angle F. Subtract from 180, I get 56. I can then set up my proportion, x over sine 78, 12 over sine 56. Move the sine 78 over, punch it in the calculator, 14.158 miles. Let's try another. Miami is 1,035 miles from Bermuda. Bermuda is 955 miles from San Juan. San Juan is 1,034 miles from Miami. Solve the Bermuda Triangle. In other words, I know the three sides of the triangle. Let's find the three angle measures. Go ahead and give this one a try. All right, so the first thing we can do is go ahead and fill in the numbers into the picture. And it doesn't matter which angle I want to find first. I went ahead and went with the biggest angle, the San Juan angle. I went ahead and labeled that S, and I set up my law of cosines in order to find the angle. The side opposite angle S would be the 1035, so that gets subtracted. The other two sides would be on the addition and in the denominator. Type it in the calculator. Make sure you type it in correctly. If you're not using parentheses around the entire numerator and parentheses around the entire denominator, it's not going to come out correctly. It should be 62.564. I can do the same thing with the Miami angle, 54.977. And then to get the Bermuda angle, I would just subtract from 180. Make sure you store those two previous numbers in your calculator. I get 62.457. The next stop on our journey would be area. So back in the day in geometry, to find the area of a triangle, you just use that old formula, 1/2 base times height. If you have the base and you have the height, you can find the area of any triangle just by multiplying them and cutting them in half. But if you're not given the base and the height, but instead you're given any two random sides and the angle between, we can manipulate that formula into something else. Now, again, I said any two random sides, so let's say it was this side, and the angle between would be angle A. Now, to find the area, it's still base times height. Base is given, but the height is not. We can solve for the height by realizing that the height itself creates a right triangle that we can then use right triangle trigonometry to solve for the height. I know that the sine of A is h over c, and I know I can multiply both sides by c to solve for the height, and then plug that in. We get our new area formula of 1/2 b for the base, c sine A for the height. In other words, 1/2 bc sine A. And I said it was any two random sides. It didn't matter which two sides as long as this angle was between those two sides. So I could also write it as 1/2 AB sine C or 1/2 AC sine B. As long as you have two sides in the angle between, multiply them, multiply it times the sine of the angle, and cut it in half. For example, 47-degree angle surrounded by a side of length 3 and 8. So I know my area formula is 1/2 AB sine C. So I can just plug and chug. Two sides are 3 and 8, angle is 47, punch it in the calculator, you have your answer. There's really no variation to this, that's pretty much all there is to that, so we're just going to go ahead and move on to the next area formula, Heron's formula. Now, Heron figured out that as long as you had all three sides of the triangle, you could figure out the area from there. You don't need specifically a base and a height, you just need the three sides. You start by finding the semiperimeter. The semiperimeter is when you take the perimeter, a plus b plus c, and cut it in half. Semi means half. And then take that semiperimeter, plug it into this formula. The square root of the semiperimeter times the semiperimeter minus one side, times the semiperimeter minus another side, times the semiperimeter minus the third side. Here's an example. Side lengths 12, 19, 23. Start by finding the semiperimeter. We get 27, and then take that semiperimeter and plug it into the formula. 27 for S, A, B, and C are 12, 19, and 23. From here, we can either plug it into the calculator as is, or we could clean it up, 27 minus 12, 27 minus 19, 27 minus 23, and then type that into the calculator. We should get 113.841. All right, let's try it again. If you are starting to realize that there's a bit of a problem with this one, you would be right. You are not making a mistake. The problem is a mistake. If I were to jump into this and get my semiperimeter of 22.05 and then plug it into the formula, hopefully you should realize right around here there's a problem. If I subtract, it becomes negative. Negative under a root means imaginary. That makes no sense when I'm asking for the area of a triangle. Area of a triangle cannot be imaginary, so we simply say not possible. Now, of course, we could have avoided all this had we remembered the rule two sides, the two smaller sides, have to add to be bigger than the larger side. And in this case, it does not pass that test, and therefore this triangle didn't exist. And I can't find the area of a triangle that doesn't exist. So if you recognize that immediately right off the bat, then you can simply say not possible. Your second clue was the semiperimeter. If the semiperimeter is less than that largest side, you can also jump straight to not possible.